All right, so 5.3, conditional probability and independence. So our learning objectives are we're going to define conditional probability, compute conditional probabilities, describe chance behavior with a tree diagram, define independent events, determine whether two events are independent, and apply the general multiplication rule to solve probability questions. All right, so what is conditional probability? So the probability we assign to an event can change if we know that some other event has occurred. So when we are trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we are trying to determine conditional probability. So the probability that one event happens given that another event has already known to have happened is called conditional probability. And this is how we are going to notate it. So it's the probability that B happens given, that line right there means given, that A has already occurred. Okay, so here's a two-way table that breaks down grades by which school of the university taught the course. Define events as E, the grade comes from an English physical science course, and the L is the grade is lower than a B. Okay, so we have liberal arts, English and physical science, and health and human services, and then grade A, grade B, below a B. So it says find the probability of L. So find the probability that the grade is below a B. So before I begin, I'm going to want to put all of these totals in so I can see what's going on. And then it makes life a lot easier. All right, so after I have all the totals, if I want to find the probability of L, that the grade is lower than a B. Well, the grade lower than a B was 3,656 times out of a total of 10,000. So that's about 36.56%. Oops. Okay, the probability that the grade comes from an English physical science course, given that it was lower than a B. So if I know it's lower than a B, what's the probability that it came from an English science course? Here, it would be 800 out of the total below B's here, because I already know it's only from the B's. Okay? So I knew it was only here. I was only looking at this part right here. So this probability would have been 800 out of 3,656. Okay, and what about this last one? Find the probability that it's lower than a B given it was an English physical science course. So given that it's here, okay, what's the probability that it's lower than a B? So that would be 800 out of the 1,600. All right. When knowledge that one event has happened does not change the likelihood that another event will happen, we say that these events are independent. Okay? So, independent events means that if I say the probability of B has already occurred, what's the probability of A? Well, it's just the probability of A, because B played no role on it. And if the probability of B occurring, given that A has already occurred, well, that's just the probability of B, because A has no role, just like B had no role. That's only if they're independent. If they're not independent, then you won't get out the probability of A here or the probability of B there. You get out something else. All right, so this question says, are the events male and left-handed independent? Justify your answer. So basically you can kind of take and do the probability of male given that it's left-handed, or you could find the probability of left-handed given that it's male. If you get that this turns out to just be the probability of male, then it's independent. If you get this to be the probability that you're left-handed, then it's independent. And that's what we want to see. So let's work this out. Which one do you want to do? Let's do the probability that's left-handed given it's a male. So given it's a male, I'm going to take from right here. So the probability of it being left-handed would be 3 out of the total of 23. So now I need to say, well, what is the probability of being left-handed? If it's the same, then they're independent. So let's see, the probability of being left-handed would be 7 out of the overall total, which is not the same, so these are not independent. You don't even have to try it the other way because we know it won't work. All right. Is there a relationship between gender and having allergies? To find out, we used the random sampler at the United States Census at School website to randomly select 40 U.S. high school students who completed a survey. The two-way table shows the gender of each student and whether the student has allergies. So are the events female and allergies independent? Well, again, you could do the probability of female given allergies or the probability of allergies given female. Pick and see what you want to do. See what you get. You can pause me. All right, so I did the probability of allergies given female. Let's see if you can look back. So given that you're female, the probability of having allergies. So the probability of allergies given female would be 10 out of the total of 23. Is that the same as the probability of allergies? Well, the probability of allergies is 18 out of 40. Are these the same? No, they're not. So they are not independent. Okay, see if you can do this. So 1 is independent because you put the card back. If you didn't put the card back, then it would not be independent. 2 is not independent because you didn't put the card back. And 3, the probability of being right-handed was 6 out of 7. The probability of right-handed, given that you're a female, is 18 out of 21. Since they are the same, they're independent. All right, tree diagrams. So it's a way to kind of show your sample space, and it's nice because you can see the probabilities. So flipping a coin twice, what's the probability of getting 2 heads? So the first thing you want to do is start by saying, after your first flip, you can get heads or tails. So this is a 1/2 probability. This is a 1/2 probability. Then the next flip is independent, heads or tails. This is a 1/2 probability. This is a 1/2 probability. So this will be the probability of heads and heads, which is 1/4. This would be the probability of heads and tails, which would be 1/4. 1/2 times 1/2. You just multiply through to get your final answer. And again, heads, tails, 1/2, 1/2. So you'd have 1/4, 1/4 overall. So what is the probability of getting 2 heads? So the probability of getting 2 heads is just 1/4. That would be head, head. What's the probability of not getting 2 heads? 3/4. So here it is, nice and neat. Not just me scribbling, but using technology. Okay. So the idea of multiplying along the branches in a tree diagram leads to the general method for finding the probability of A and B. The two events happen together. So I know the probability of A and B is the probability of A times the probability of B given A. And this is in your formula sheet. All right, so how to make a tree diagram. Maybe it's gonna play. No, it's not playing. All right, Well, I will take you through what I wanted to show you. Okay, when you go and make a tree diagram, let me go back actually so I have more room. Let's say this is A, this is C, then you could have B, D, E, F, or something like this, okay? So this guy right here is the probability of A. This is the probability of B given A has occurred. And when you multiply them together, you get the probability of A and B. So in a tree diagram, you follow through to get the probabilities. So this means the probability of A times the probability of B given A is equal to the probability of A and B. And that's what you have for your formula sheet. So let's do it on a different branch. Let's say here we started with the probability of C. And this guy would be what? That would be the probability of F given C has already occurred. So overall, that would be the probability of C and F. So that's your basis of a tree diagram where all the parts come from. All right. The Pew Internet and American Life Project finds that 93% of teenagers ages 12 to 17 use the internet, and 55% of online teens have posted a profile on social networking site. What percent of the teens are online and have posted a profile? So what we're going to do is make a tree diagram. So first I know, I'm just going to randomly select, and we have event A of being online and B of not being online, basically. So it told us that 93% are online. These have to total 1, so you have 7% left. Then, if they're not online, then they cannot select a profile. So 0 could say yes here, only 1 could say yes here. So now I know that this probability would be 0, this probability would be 0.07. 0.07 times 1 and 0.07 times 0. Okay, from up here it says if they have selected a profile, it'd be 0.55. So 1 minus 0.55 means that 0.45 is left. So what are these probabilities? Well, you would take 0.93 times 0.55, and this is 0.5115. In this one, you'd go 0.93 times 0.45. This is 0.4185. When you add all of these probabilities on the right together, what should you get? 1. Okay. So what percent of teens are online and have posted a profile? That'd be this right here, which was 51.15%. So this again is the probability of being online. This is the probability of posting a profile given that you're online, and this is the probability of posting a profile and being online. All right, let's try this one. See if you can get what I got. Just kind of use it as a reference, read through of making your own. So you first start with adults 18 to 29, 30 to 49, and 50 plus. So 27% were in the first, 45% and 28%. Total 1, you're good. Then it says the Pew Internet American Life Project finds that 70% of internet users, so you're on the age from 18 to 29, 75 have visited a video sharing site, or sorry, 70. So then what's left is 0.3. Keep going and see if you can figure all of this out. See if it all makes sense. And then it says, what percent of all adult internet users visit video sharing sites? So this one, and this one. So add them all together. And you get 49.13%. Okay, About 55% of high school students participated in school athletic team at some level, and about 5% of these athletes go on to play a college team in the NCAA. What percent of high school students play a sport in high school and go on to play a sport in the NCAA? So, high school athletic team, yes, and no. So it says 55%, which means 45% would be left. So if they don't play, so this would be in the NCAA, right? Yes, no, yes, no. So I know that this would be 0, because if you don't play here, it says, well, I guess you could go on. I don't know that actually. Sorry, you could still go on. So they don't tell me that part, but let's see what else they do tell me. About 5% of the athletes who participate here go on. So this would be 0.95. All right, so let's see if that's enough to answer. What percent of high school students play a sport in high school and go on to play? So in this case, that would be your 0.55 times your 0.05. I'm sorry, which was 2.75%. Okay, here's more practice if you want it. And let's just see how you do. And the answer. Here's some more. See how you do if you'd like to. And here's your answer. All right. Independence, a special multiplication rule. When events A and B are independent, we can simply multiply to get we can simplify the general multiplication rule, since we know the probability of B given A is just the probability of A for independence. So if they're independent, then you can just take the probability of A times the probability of B. Okay. So following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rocket was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly, so functioning properly, was 0.977. Assuming O-ring joints succeeded or failed independently, what's the probability that all 6 would function properly? So all 6 functioning properly would be that we have properly times properly times properly times properly times properly times properly. So all 6 being proper, you just multiply across and you'd get 0.87. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So, to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is is independent on his or her performance in other innings. Independent. All right, so 9 perfects in a row would be 0.4 times 0.4 times 0.4 times 0.4, 9 times, or you could think about that 0.4 to the 9th, which is a really unlikely chance. So that's 0.026% even. Okay. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive test result. Among 100 women with normal pregnancies, what is the probability that there will be at least one false pregnancy? So this one's a little bit different. So if you have 100 women with normal pregnancies that are tested, and you want to know what's the probability that there's at least one woman who will receive a false positive. So at least one would be 1 minus the probability that no positives happen. So no positives happen, so 1 minus the probability that no positives happen would be 0.95. So you could take now your 0.95 to the 100, multiplying it out 100 times by itself, and this is the probability that at least we have this would be the probability of none of them being positive. So the probability that at least one positive would be 1 minus that. So these are none are positive. Okay? Okay, so think about it. Is there a connection between mutually exclusive and independent events? So mutually exclusive would mean that they have no overlap. Independent means one doesn't affect the other. So let's think about this. Choose a U.S. adult at random. Define event A as the person is a male. Event B as the person is pregnant. Well, it's pretty clear that these two events are mutually exclusive. They could never, ever happen together. Hopefully. What about independent? If you know that A has occurred, does this affect the probability that event B happens? Of course. We know if a person is male, then the chance that the person is pregnant is 0%. These two events are definitely not independent. So these would definitely be dependent. So, two mutually exclusive events can never be independent because if one happens, the other event is guaranteed to happen. All right, so two mutually exclusive events can never be independent. Mutually exclusive tells me that they have to be dependent upon each other. All right, see if you can answer this guy. And you can check your answers. Let me know how you did. All right, so calculating conditional probabilities. So using the formula, we have this on our formula sheet, you can just rearrange, again, multiplying or dividing things over. And you can look and just find what the probability of B given A would occur if they are not independent. All right, so here, who reads the newspaper? In section 5.2, back there we noted that residents of a large apartment complex can be classified based on the events. Reads USA Today, reads the New York Times, and the Venn diagram below describes the residents. What's the probability that a randomly selected resident who reads the US Today also reads the New York Times? So, what's the probability that they read the New York Times given that they read the USA Today? Is basically what this question is asking. So use your formula sheet, get your conditional probability. So here you want to use the probability of New York Times and the probability of USA Today, which is 5%, divided just by the probability of USA Today, which was 40%. Simplify that. And you should get 12.5%. So there's a 12.5% chance that a randomly selected resident who already reads USA Today also reads the New York Times. All right, let's look at this one. U.S. households are classified according to the types of phones they use. See the two-way table below. What is the probability that a randomly selected household with a landline also has a cell phone? So you're saying, what's the probability of having a cell phone given they have a landline? See if you can do that one. I got 77%. False positives in drug testing. Many employers require prospective employees to take a drug test. A positive result on this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs. And the false positive rate, so use drugs, would be 4%, and don't use drugs would be 0.9%. So getting a positive result, where am I at? The false positive, so they do not use drugs, but they got a positive, is 5%, so this would be 0.95. And the false negative would be 10%, so this would be 90%. What percent of people who test positive actually use illegal drugs? So people who test positive and are using drugs would be this right here. So 0.04 times 0.90. So, sorry, let me look. So this would be just put it in my calculator, 0.036. So let me just make sure I did this right. What percent of people who test positive actually use illegal drugs? So they tested positive. Oh, sorry. I just filled this in wrong. Okay. Backtrack, erase. Crazy Mr. Rose. So it said that suppose that 4% of all prospective employees use drugs and the false positive rate is 5%. So my false positive is 5%. So positive, negative, negative. So false positive means they got a positive and it was 5%. And false negative was 10%. That was false negative. Okay, sorry, we had it right. All right, long day today. Okay, so we had this started right. So this right here we said was let's fill this in, 0.036. And then 0.04 times 0.1. And 0.9 times 0.05. And 0.9 times 0.95. And all of those should add up to 1. You can double check. That's what I'm going to do. So we have 0.855 plus 0.045 plus 0.004 plus 0.036. Yikes, what do we do? 0.04 times 0.9. 0.04 times 0.1. 0.9 times 0.5. Oh. 0.9 times 0.05. And 0.9 times 0.95. 0.855 plus 0.05. Okay, sorry, when I erased that was a 96, so those are different. That's why we always check ourselves. So 0.96 times 0.05 would give me 0.048. And 0.96 times 0.95 would give me 0.912. Now those should add up. 0.048, 0.004, 0.036. Okay, sweet. Woo, 1. My goodness. Okay, so now it says what percent of people who test positive actually use illegal drugs? So testing positive would be this and this. And that they actually use illegal drugs was 0.036 out of 0.036 plus 0.048. Okay, sorry, that one was crazy. But we're good. And simplify that down. And you should get 42.9%. So we are done after that crazy problem. Summary of 5.3. And we're done with Module 5. Sweet.